ichizero.
For those who already know, it might honestly be a boring story. However, for me it was all quite new, so I'm doing this with the hope that I can explain it as clearly as possible. This is going to be quite a serious discussion. However, even when proper research has been conducted, there are still things that make you go, huh? Is that some kind of urban legend? The thought experiment called Schrödinger's cat. The interesting part about that story is how it combines the concept of a single quantum with a macro concept like a cat. But you don't perceive it that way, do you? The conversation is about how it's interesting to think that if you put them together, they should interact, and this kind of gimmick or mechanism will occur.
I've heard that the story of Schrödinger's cat was created as a paradox to point out flaws and doesn't really have any particular meaning. Is that true?
That can be said for the whole situation. In short, the perspective is different. Quantum mechanics is basically used for making industrial products. From the perspective of such a person, that's meaningless. It doesn't matter, because the calculation results will definitely match. Isn't it the difference between someone in that position and someone who wants to know the truth? Therefore, for people who want to know the truth, those kinds of paradoxes are interesting. Because of doing that paradox, there were also new discoveries, weren't there? Therefore, in that sense, I think it's a very meaningful consideration.
I think considering that paradox is amazing.
Amazing. And then someone goes and solves it. That's why pursuing paradoxes is really meaningful, isn't it? That's why having two perspectives is really important. Because you lump it all together, a lot of people end up saying unnecessary things. Isn't it only natural because we're in different positions? There are plenty of people for whom it's pointless to think about paradoxes. If you say that, then we wouldn't be able to make any industrial products at all. The practical range, in other words, the matter of interpretation, is not considered. That's why students don't really think about interpretation. Professors probably don't make you think about interpretations and such, because it's pointless. Because they use formulas to analyze something, or to obtain some results, don't they? Of course, I think it's perfectly fine for people who want to come up with new physical theories to pursue that as much as they like. Most students aren't like that, and there's no point in thinking about such things while you're still learning. You need to understand that. This needs to match the calculation results, and you need to understand the reasons why it holds true. So the main focus this time is whether to accept or not accept the proposal. This is the accepted history, quantum theory. Let's try accepting something like that for now. Once you accept it, you'll find yourself repeatedly thinking, huh? Things are going according to plan. So, it's like accepting physics after all. That's because this quantum mechanics is based on experiments. There's a sense in which the theory was built up from the experiments. Of course, there is verification. But quantum theory was built more from the perspective of when we conducted an experiment. This is the result we got, using that as a hint to construct the theory. But in reality, whether you can feel it or not, there are calculation results. And the fact that a product is completed based on those results is truly astonishing. I think humans are crazy. No, really. Quantum theory, the science of monism. The principle of complementarity refers to the concept that two seemingly incompatible things can complement each other to form a single entity or world. A thorough examination of the worldview of quantum theory. First of all, semiconductor devices used in electronic equipment. The physical laws governing that realm are precisely quantum theory. So it's not something suspicious or anything. We are already using it quite a lot. It is not an exaggeration to say that semiconductors are the crystallization of quantum theory. The motion of macro objects, such as the Earth's revolution around the Sun, rockets, airplanes, and automobiles, can be calculated and their outcomes predicted using the classical mechanics developed by Newton. However, in the small world of molecules and subatomic particles, Newton's classical mechanics can no longer be used. It does not provide correct results. Therefore, quantum theory is used not only for semiconductors, but also for determining the structure of genes and DNA. Additionally, phenomena like nuclear fission reactions and nuclear fusion reactions can also be predicted using quantum theory. The subject matter that quantum theory deals with is the world that is approximately less than 1/10,000,000th of a millimeter. Quantum theory, when compared to the theory of relativity, can be said to far surpass it in terms of practicality. First of all, quantum theory considers microscopic matter as waves. However, it's a bit different from the waves that we imagine can form on water. The waves of water are the result of the collective motion of water particles moving in a wave-like manner. But an electron, which is a type of quantum particle, exhibits wave-like properties even on its own. It's a state where waves appear as particles, or rather, it's a state where waves are perceived as particles. To begin with, a wave is a phenomenon, not a thing. For example, sound is a phenomenon where variations in air density are transmitted, so it is obviously not a physical object. It seems that electrons exist in a wave state when we are not observing them. When we observe them, electrons always behave like small particles. The observational fact is that it is observed as a particle. No matter how high performance a microscope we use, we cannot see electrons, which exist in a wave state. No one has ever seen it, and it is likely that no one will be able to observe it in the future either. With Schrödinger's equation, the results of any experiment involving electrons can be predicted remarkably well. Precisely. Therefore, in practical terms, a theory that currently uses quantum theory without any problems is what we refer to as quantum theory. Regarding the meaning of the word quantum, it refers to an amount of energy, a small chunk, or a unit. As a term, quantum theory expresses that way of thinking or philosophy. Quantum mechanics is a mathematical means of describing physical phenomena based on quantum theory. First, I would like to talk about the true nature of light. In fact, the word quantum originated from the study of light. A German physicist named Planck proposed a theory called the energy quantum hypothesis. This hypothesis was discovered while exploring the relationship between the temperature of a substance and the color of light emitted by the substance. Therefore, it can be said that quantum theory was born from the study of light. Light has been the subject of debate among many scientists for centuries regarding whether it is a particle or a wave. First, the famous physicist Newton proposed the particle theory of light. The claim is made that light must be made of particles. When light is shone on an object, a clear shadow is cast behind it. If light is a wave, then waves have a property called diffraction, which means they bend around obstacles and don't produce sharp shadows. Newton argued that the outlines should become blurred. If you imagine the waves of water, it's easy to understand, but it's difficult to have a clear distinction in places where there are no waves. Somehow, the waves end up being roughly formed. Next, the wave theory of light, which posits that light is a wave, emerges. It was thought that light is a wave because, even if you intersect two thin beams of light, they pass through each other. If they are particles, they should collide and change direction or reflect when they cross paths, right? The idea was that since they do not interfere with each other, this is likely to be a wave. It is known that waves on water continue to move straight, even if they collide with each other. They don't bounce back, do they? In this case, one might argue that waves wouldn't create shadows. But when there's a significant difference in size between the wave and the obstacle, specifically when the wave is small and the obstacle is large, diffraction does not occur. In other words, the wave does not bend around the object and is instead blocked by it. Therefore, even if light is a wave, if it is a very small wave, shadows will be properly formed. That's the way of thinking. What is a wave in the first place? Waves are composed of roughly these three elements: wavelength, amplitude, and frequency. Wavelength refers to the distance between the peaks of waves, as waves undulate up and down. It is the length between the peaks and also between the troughs. The number of times those peaks and troughs repeat in 1 second is referred to as the frequency. Amplitude refers to the depth of the peaks and troughs, doesn't it? Waves with larger amplitudes have greater energy. This is similar to the waves that occur in water. Just like water waves, the higher they are, the stronger their force becomes. The term wavelength refers to the same concept as frequency, but mathematically, these two have an inversely proportional relationship. It's like waves with longer wavelengths have lower frequencies, and waves with shorter wavelengths have higher frequencies. The next point is the definitive evidence that light is a wave. The phenomenon known as interference of light is discovered. This interference is a phenomenon characteristic of waves. So, because phenomena characteristic of waves appeared in light, it was concluded that light is a wave, right? Wave interference refers to the phenomenon where the crests of two waves overlap, causing the wave's amplitude and height to increase significantly. This occurs when the waves combine, resulting in taller crests or deeper troughs. Conversely, when a crest and a trough overlap, they cancel each other out, causing the wave to disappear. That is what we call a wave. The physicist Young confirmed this interference phenomenon through the double-slit experiment. In this experiment, a board with two narrow slits is placed between the screen and the light, and the light passes through there and is projected onto the screen, and this describes the observation of how the light is illuminated. On the screen, there were interference fringes with alternating bright and dark areas. The reason interference fringes are formed is that light propagates radially like a wave, and when it reaches the screen, the parts where the peaks of two waves overlap experience an increase in wave amplitude due to interference. So that means that part becomes even brighter. On the other hand, in the parts where the peaks and troughs of the two light waves overlap, the waves cancel each other out due to interference, resulting in darkness. So that means stripes are formed. As a result, it is thought that interference fringes were formed, just like with waves, if light were particles, right? On the screen, there should be a long, narrow band of light, just like the slit. In short, the particle theory could not explain the reason why stripes are formed. It was later discovered that electric currents produce magnetism, and magnets produce electric currents, leading to the understanding that electricity and magnetism are closely related phenomena. And then, physicist Maxwell predicted that the electric field, which is a space where electric forces operate, and the magnetic field, which is a space where magnetic forces operate, propagate through space while oscillating. This refers to the waves of electricity and magnetism. In other words, electromagnetic waves. The measurement of the speed at which these electromagnetic waves travel through space showed that it was the speed of light. Therefore, Maxwell argued that light is a type of electromagnetic wave, and soon it will be proven by the physicist Hertz. After that, electromagnetic waves are given various names depending on their wavelengths. For example, visible light, infrared rays, ultraviolet rays, microwaves, X-rays, and radio waves are all electromagnetic waves. The names and usage ranges of electromagnetic waves are determined by their frequency. In other words, the difference in wavelength. Electromagnetic waves with wavelengths ranging from 380 to 770 nanometers can be perceived by the human eye. These are what we refer to as light. As a result, it means that we are able to perceive electromagnetic waves as light. The first question under More Questions About Light is about what the medium of light is. Basically, waves do not propagate through empty space, right? Waves do not occur in empty space. If light is a wave, then there must be a substance that plays the role of transmitting its vibrations. For sound waves, the medium they encounter is air. Sound waves are transmitted as nitrogen and oxygen molecules in the air vibrate. Therefore, sound does not travel in outer space. This raises the question, how does sunlight reach the Earth? If light is a wave, then there would need to be a medium for light to fill the vacuum of outer space. So if it were a vacuum, it wouldn't be able to propagate, right? Quantum theory originated from the motivation to accurately know the temperature of iron in a blast furnace. It originated from research exploring the relationship between the color of light emitted by a substance and its temperature. In the past, it seems that people relied on their artisanal experience and intuition to judge the temperature of molten iron. They would think that if it was a dark red color, it was about 1000 degrees Celsius. If it was red, about 2000 degrees Celsius. And if it turned white, it was above that. As a method to measure it accurately, it seems that Planck tackled this problem. To begin with, light contains various colors of light. Strictly speaking, it includes light of various wavelengths. Color is an interpretation made by the brain. We recognize the color of an object as the brightest color among the colors of light that enter. Therefore, various colors are coming in, but it means that the strongest one is being recognized. By the way, among the light visible to humans, purple has the shortest wavelength and red has the longest wavelength. The difference in the color of light is due to the difference in the wavelength of electromagnetic waves. The fact that red appears as red to humans is actually just a matter of interpretation, a human issue. The act of examining what wavelengths of light are contained within a single light and how strong each one is called spectral analysis of light. This spectrum refers to the meaning of separating mixed things. Next, the energy quantum hypothesis comes up. The energy quantum hypothesis is a groundbreaking concept introduced to physics, proposing that the energy of light is discrete and discontinuous. The physics up until then did not understand that light energy is discrete. It was thought to be continuous. The reason for this is that the degree of discreteness was too small, making it appear continuous. The degree of discreteness is an extremely small amount, specifically 10 to the power of minus 20 of the light energy. They're almost stuck together, so it seems like you can't usually tell them apart. For example, it's like thinking you were going up a slope, but when you look closely, it turns out it was actually a 1 millimeter step. There are differences and perspectives that arise due to this scale, aren't there? This might be what you could call the difference between classical physics and quantum mechanics, though this is a rough explanation. It might be helpful to imagine the difference between a human using these stairs and an ant using them. When humans use it, it's a slope, but when ants use it, it's like stairs, because it's only 1 millimeter. If humans are Newtonian mechanics, then ants are quantum mechanics. For example, whether you take the perspective of an ant and calculate the shortest distance by incorporating the number and height of these 1 millimeter steps into a formula, or you take the perspective of a human and view these steps as a slope and calculate the shortest distance as a single edge, I think you would get the same result. However, from a human scale, it's pointless to go through the trouble of incorporating the number of these tiny steps and their respective heights into a formula for calculation. It would just be an incredibly difficult task. This is also the case with actual quantum mechanics. Conversely, from the perspective of an ant, a practical viewpoint is a 1 millimeter step. For the ant, it's important, but for humans, it's something trivial. Then naturally, since it needs to be regarded as stairs, as an ant would see it, if it is not calculated as a discrete form of steps, it will not be calculated correctly. On the contrary, the ant sees these stairs as a slope. If you do that, you'll end up arriving at an incorrect answer and have a perspective that is extremely different from reality, which isn't practical for ant. We don't look at it that way, do we? Stairs are just stairs. For an ant, things like the differences in each step or the surface area are probably important. When you hear this, you get the sense that the world of quantum mechanics is not particularly mysterious. Conversely, it becomes understandable why the behavior of quantum physics does not occur in the macro world that we can perceive. I think it's fine to accept that it's just a difference in perspective. Next, I would like to talk about the photoelectric effect. Einstein focused on the electrons that are emitted when electromagnetic waves are applied to a metal, and through the light quantum hypothesis, he concluded that the relationship between the intensity and frequency of light corresponds to the relationship between the quantity and quality of light. Light with a high frequency has photons with a lot of energy, so electrons are ejected with great force. The idea was that strong light has a large number of photons, so the number of electrons that are emitted is also large. In this way, Einstein succeeded in elucidating the mechanism of the photoelectric effect by reconsidering light, which was thought to be a wave, as a collection of particles called light quanta. If we can think of light as particles, then the question of what the medium of light is, which we discussed earlier, is also resolved, isn't it? It was understood that while waves cannot travel through a vacuum, particles can, so it's okay for them to do so. It has come to be understood that light exhibits a seemingly mysterious duality, being both a particle and a wave. I'll say it again, but it's not that the particles themselves are waving, moving, or undulating. Please remember here that these are waves with different properties than those that form in water. To summarize up to this point, initially, the idea that light is a wave was dominant due to phenomena such as light interference. The scholar Planck studied the relationship between the temperature of a heated object and the spectrum of light it emits, and proposed the energy quantum hypothesis, which states that the energy of light takes on discrete values. Einstein proposed the hypothesis known as the light quantum hypothesis, which suggests that light is a collection of small particles, in order to explain the photoelectric effect. It becomes clear that light exhibits a duality, possessing both particle and wave properties. Up to this point, I suppose we've been talking about the concept of quantum being born. Next, I will talk about the structure of atoms. All substances are made of atoms, aren't they? The size of an atom depends on the type of atom, but it is said to be approximately 1/10,000,000th of a millimeter. Incidentally, it is only very recently that we have been able to directly observe the shape of atoms. In fields such as chemical reactions of substances, I believe it has been utilized quite extensively. Shortly after the atomic theory, electrons were discovered. And it was also understood that these electrons are contained within atoms. From around this point, it becomes clear that atoms are not indivisible and actually have even smaller structures. And it was understood that an atom consists of a nucleus, which contains protons with a positive charge and neutrons with no charge. And around this nucleus, there are electrons with a negative charge. After that, as we explored the behavior of electrons and electromagnetic waves, in other words light, it became clear that quanta behave in a manner completely different from the previously considered physical laws and structures. At this point, I think this theory is full of flaws, but in terms of introducing the concept of quantum into the atom, it contributes to a groundbreaking step forward for later quantum theory. From here, we'll be introduced to one astonishing and outlandish idea after another that will leave us speechless. Quantum theory is truly a wonderland, isn't it? Why does such an extraordinary and mysterious world exist from our perspective? As I mentioned at the beginning, it's because there are facts that we still don't know or cannot see. This is obvious. But things that we cannot see now will remain unseen in the future. You think that's not the case, right? However, our potential or capabilities don't really improve, do they? We can only see by light entering through the eyes and being received by the retina. We can only see optically. Aside from that, it is likely something created with computer-generated imagery or through predictive models. So even if we want to see it, we cannot. There are limitations to this. The majority of the microscopic world that we perceive is not something we directly see. Rather, we are looking at a world depicted by some kind of mathematical model. In short, the quantum world can only be visualized by observing the values of electromagnetic waves and using mathematical models to create images of them. I would like to talk about the wave that cannot be seen when you try to look at it. The physicist Louis de Broglie came up with the groundbreaking idea that electrons are waves. Earlier, we talked about light being a wave, but it turns out that electrons are also waves. And then, they came up with a model where the wave of electrons orbits around the nucleus. The wave does not exist at a single point, but rather, it exists with a certain extent or spread. So, what exactly is the nature of an electron's wave? The answer will soon be revealed through a certain intriguing idea from this kind of research. To put it simply, the wave of electrons is like the dice that God rolls. This is referred to as the probabilistic interpretation of the wave function. The probabilistic interpretation of this wave function was proposed by the physicist Born. For example, let's put a single electron inside a box and confine it. If we consider electrons as waves, then electrons exist with a spread within the box. Here, a divider was placed in the middle of the box to split the space into two sections. In that case, the electron's wave should also be able to be split into two. If it's a wave or something like mist, it should be possible to split it. However, there was only one electron placed in the box, right? It is understood that electrons are the ultimate particles. In other words, elementary particles. In short, it means understanding that it cannot be divided. It is absolutely impossible to further divide a single electron. Such experiments cannot actually be conducted, so they remain thought experiments, but contradictions can be identified. In this experiment, when one electron is placed inside a box and divided by a partition, the electron should definitely be found in one of the two spaces. Now then, in this case, the question is, what exactly is broken? An electron cannot be split, but it can be divided in half. This is expressed as the probability of where the electron will be found in space being distributed. The separation is based on probability, isn't it? This is what is called the probabilistic interpretation of the wave function. It's a very practical way of thinking. And in other words, it's a very clear-cut approach that focuses solely on practicality while turning a blind eye to everything else. Where a particle like electron can be found, what kind of energy that electron possesses, and what phenomena it causes. Once that is understood, since it allows us to explain all experimental results, it means that at this point, predictions at the microscopic level have become possible, and it has become a sufficiently practical theory. So, it's actually being used in industrial products, isn't it? In a sense, as long as the theory can accurately predict experimental results, that's sufficient. Conversely, it means we don't need to concern ourselves with what the wave of electrons, which doesn't appear in experimental results and is thus invisible to us, represents. Next, I will talk about how the wave of electrons converges. Although it is not a wave, it spreads out like a wave, and what is considered an electron can only be determined by probability in that location. However, when observed, the location can be precisely identified. Therefore, it is thought that electrons spread out like waves only when we are not observing them. This state is expressed as being in a state of superposition. When the wave of an electron is spreading out, we think of it as the electron being in a superposition of states, where it is in one location and also in another location at the same time. Or, in other words, you consider them to be coexisting. However, this does not mean that an electron exists in multiple places simultaneously. When there is a single electron, it definitely exists in one of the two places, but we don't know which one, or we can only say it probabilistically. It's a little different from that kind of thing. In any case, the state where a single electron is in multiple places is a state where the same electron is overlapping within itself. This overlapping is referred to as superposition, meaning that electrons can exhibit behavior that goes beyond the ordinary concept of position. When we are not observing the electron in this way, the electron's wave is spread out and in a state of superposition. However, when we observe an electron, the electron's wave instantly collapses. For example, although I can't see it so I'm not sure, something that was moving like a wave contracts, and the wave that spread out suddenly shrinks at a certain place. This is being regarded as a point, or a particle, isn't it? In terms of the wave function, once an electron is observed, it becomes definite, meaning it is in a 100% certain state. In short, once it is found, the possibility of it being anywhere else, in other words, the possibility of finding the electron in another location, naturally becomes zero. This is referred to as the superposition state being resolved. However, as I have said many times, even though the position of an electron is determined probabilistically, it does not mean that the electron's position is actually predetermined at one specific location, and we can only estimate that location probabilistically. Bohr thought that the position of an electron is determined probabilistically, as if rolling dice, with the location where the electron is found being decided by a kind of element of chance. It looks similar to a statue game, so to speak. When you look, everyone is perfectly in place, but when you're not looking, it's like everyone is bustling around. It's the same kind of feeling. What we can observe allows us to engage in science with an understanding of, so that's how it works. However, the world that we cannot see, like the wave of an electron or contraction that does not manifest as a phenomenon, cannot be discussed scientifically. It should be different from our senses, right? It seems that the only option is to interpret it that way. Next is the Copenhagen Interpretation. Up to this point, we have come to understand that substances in the microscopic world, such as electrons, are governed by completely different rules from the physical laws we were familiar with. This is not something like another world. It's not that the rules suddenly changed when we became smaller. Originally, it's not like they could use magic over there and we couldn't over here. It's simply a matter of us not knowing. In the microscopic world, there are phenomena and rules that we cannot perceive. And on top of those rules, the physical laws that we know also exist. To put it in extreme terms, I think it's possible to perform ordinary, general physical calculations using quantum theory, deliberately using quantum theory. For the ant, it's a staircase, but for us, it's a slope. In the same way, it's no different from events occurring in the same physical world. The role of science within civilization is to make predictions, and in making predictions, the question is how it would be if we indeed used an ant-based mathematical model for predictions. It's incredibly difficult, to the point where it's not just difficult, but almost an impossible game due to how detailed it gets. It becomes complicated. This isn't realistic, is it? Therefore, quantum theory is not used in the macroscopic context. It is quite natural to use a suitable or optimal practical mathematical model according to the scale of the forecasting needs. So, I want you to remember that it's not really about which one is right or wrong in the first place. That being said, once you introduce a principle like the probability in quantum theory into physics, no matter how practical physics may be, it ceases to be deterministic. Isn't determinism important? For example, it's impossible for someone to disappear just by turning around, right? For us, probability theory and determinism are antonyms, aren't they? At the very least, the natural phenomena around us do not behave according to probability theory, do they? Sometimes this guy disappears, you know. That doesn't happen, right? When you let go of a ball from your hand, the probability of it falling to the ground is about 70%, and it doesn't become something like a 30% chance of it soaring into the sky. It's not like you would randomly say, oh, today it went up. Therefore, when we are told that which one it will be is decided by rolling a dice, we can't help but wonder, can that really be called a law? Can it be called a rule? Under the same conditions, we can consider something a rule or a law precisely because it results in the same outcome. The quantum theory at a glance keyword I thought of is that physical phenomena seem to be represented deterministically to us. I'll say it again. But if this probability theory were due to us not knowing the rules, causing us to be unable to determine the exact location of an electron, that might be understandable. However, probability theory actually indicates that the future is determined only probabilistically. When electrons are perceived as waves, their behavior can be explained. Conversely, this means that without perceiving electrons as waves, the current behavior of electrons could not be explained. Therefore, it is only circumstantial evidence that electrons are waves. Therefore, in order to draw a scientific conclusion, we would like to have more powerful and definitive evidence that demonstrates electrons are waves. Evidence from the double-slit experiment. Using a device called an electron gun that emits an electron beam, electrons are directed towards the screen. This is the electronic version of the experiment I briefly introduced at the beginning. Initially, it was the light version, and now it's the electronic version. The screen is coated with a phosphorescent material, and when incoming electrons hit it, the spot lights up. This is the kind of device we create. This is an experiment where a plate with two narrow slits is placed between an electron gun and a screen to observe how electrons actually behave. In this experiment, we create a state where only one electron is present and conduct an experiment where a single electron is emitted. From the results of the experiment, it can be understood that the wave nature of the emitted electrons, in other words, the wave properties, are not waves that arise as a result of collective motion like ordinary waves, but are properties of individual electrons. The image that a single electron creates on the screen is nothing more than a small dot. But when these images are superimposed, interference fringes, which are evidence of wave-like behavior, appear. However, actually this is a bit strange. Interference waves are a phenomenon that occurs when two waves overlap, right? They don't occur with just one wave. In this experiment, electrons are being emitted one at a time. How does a single electron interfere? It's mysterious, isn't it? It seems that a single electron interfered with itself, meaning that the electron in the state of having passed through the right slit and the electron in the state of having passed through the left slit of the double slit interfered with each other. This can be put another way. The electron passes through the left slit while also passing through the right slit, and the two interfere with each other. In other words, the electron interferes with itself. This means that it serves as evidence that the state in which the electron passes through both slits is in a superposition. When two states overlap within a single electron, interference also occurs in the electron state. Until the electron reaches the screen, that is, while it is not being observed, it is in a wave state, or a state of superposition, where its position and form are in a probabilistic state. That's why you can go through both. This is all true. With this, it has been experimentally proven that electrons possess both particle-like and wave-like properties. Now, I would like to discuss the question of why similar things do not occur in the macro world as we know it. Why are wave properties not observed in a baseball? The reason is that the waves possessed by large objects around us have wavelengths that are too short. And as a result of observation, we can naturally only see the waves in a collapsed state. Therefore, the wave-like properties of such objects do not clearly manifest. The wavelength of the wave that matter possesses, known as the matter wave, is said to be approximately 10 to the power of minus 33 meters. This means it is extremely small. This is the size of an atom, 10 to the power of minus 10 meters. It's an extremely small size, a trillionth of this, and then another 100 billionth of that. It is understood that the larger the mass of a substance, the shorter its wavelength becomes. Even though we call it a wave, it essentially becomes something akin to a point with almost no spread. Compared to this, electrons, which have much smaller mass, become relatively large waves compared to themselves. Therefore, when considering the motion of electrons, it becomes impossible to ignore the fact that they can be in various positions. For these reasons, when dealing with a world that is the same size as or larger than an atom, the wave-like properties hardly appear. Therefore, it is sufficient to consider their motion as particles, as in classical physics. So, it means that things will go according to plan in this situation. Recently, with advancements in experimental apparatus, it seems that there has been success in creating interference patterns with relatively large molecules. No matter how large a substance may be, ultimately it is a collection of microscopic substances. Therefore, there is no boundary between the microscopic and macroscopic, and it should be possible to observe wave-like properties even in larger substances. Next, the uncertainty principle. In the earlier double-slit experiment, there is a slit between the gun and the screen, essentially on the way to the screen. So, what would happen if we observed the electrons at about the exit of this slit to check whether they are passing through both slits? Regarding this, physicist Feynman conducted a thought experiment. It's an experiment where you set up an observation device right where the slit plate emerges and conduct observations. In this case, the photon emitted by the observation device, or the light, collides with the electron and returns the observation result. However, due to the collision of the light, the position of the electron becomes determined, doesn't it? That's why when you observe, it becomes certain. As a result, the electron, which should have had the possibility of existing in both places simultaneously, ends up being confirmed to have passed through only one side, not both. When conducting this experiment, interference fringes, which are a characteristic of waves, should not appear on the screen, right? It's already confirmed. So at this point, it's certain that it passed on the right side, but not on the left side, right? In that case, since there won't be two anymore, interference fringes shouldn't appear. What this makes clear is that in response to the question of whether the electron really passed through both slits, it cannot be confirmed through experimentation. The only way for us to observe is to have light collide with those electrons. Therefore, it exerts a considerable influence on the object, which is the electron. In contrast, in the macroscopic world, the changes caused by the collision of light are too small, so even if its position changes slightly, it results in negligible changes. To tell the truth, there are quite a few drawbacks like this in micro experiments. To put it simply, when you want to measure the temperature of water in a cup, you use a thermometer, right? At the stage where you insert the thermometer into the water temperature changes due to the influence of the thermometer, doesn't it? It shouldn't be a problem if it's about the size of a large pool. For example, if you try to measure the temperature of a single drop of water with a thick thermometer about the width of a finger, the temperature will change in no time. It's difficult to measure the correct temperature. It means that the same thing is going to happen. In other words, the smaller the object, the more observing it changes its state, making it very difficult to know its actual state. The physicist Heisenberg presents the uncertainty principle, which explains the unavoidable ambiguity in the microscopic world. This is about measuring the position and momentum of a certain substance. When you measure the position and the movement of that substance, you cannot simultaneously determine both with a single value. If I were to use an analogy, it's like trying to determine the position of a spinning propeller. When you take a photo to observe it, the position becomes certain, like, oh, it's right here. However, looking at that photo, you can't tell how fast it's spinning, right? That's the situation. So this time, I'm going to try measuring the speed, attempting to measure speed by tracing the path of the propeller. When you do that, you can't pinpoint the position of the propeller, can you, as information? The uncertainty principle is something like that, isn't it? Next, does the moon only exist when it is observed? Einstein pointed out a certain paradox in quantum theory. It is known as the EPR paradox. When a certain particle splits into two and flies apart, suppose one of them rotates to the right. If one rotates to the right as a result of the split, the other will rotate to the left. Furthermore, each of those particles continues to move farther and farther away. Eventually, they are 1 light year apart. At that time, one of the particles is observed. Then, it is determined whether it is spinning to the right or to the left. Fly away, and if no one is watching, you won't know which way it's turning. But if you look at just one side, it becomes certain. When that happens, the direction of rotation of the other particle, which is 1 light year away, is instantly determined at the same time as the direction of rotation of the observed particle is decided, even though they are 1 light year apart. This is equivalent to particles that are 1 light year apart, instantly transmitting information to each other. This was something that Einstein found unacceptable, because it contradicted Einstein's principle of the constancy of the speed of light. So he thought, no, something's wrong. Einstein passed away before this question was resolved. Subsequently, through the experiments conducted by physicist Aspect, it was proven that even if particles move to a faraway location, as long as they move without being observed, the spin directions of both particles are determined simultaneously, even if they are a light year apart. Einstein reportedly said that if the claims of quantum theory are correct, then the moon is there, because we see it, and when we don't see it, it isn't there. This gigantic moon, or speaking of the macro world and the quantum world on the same level, is certainly not possible, but I roughly understand what you are trying to say. We believe without a doubt in the existence of objective facts. When I turn around, I don't think there's nothing behind me. To begin with, the objective facts that we envision or perceive are indeed true and not incorrect in the macroscopic world, or so I believe. That being said, when we closely examine the very substances that make up our being, it is an undeniable fact that there is not a single definite fact accompanied by objective reality in that world. In this way, Mr. Bohr explains the characteristics of the view of matter and nature that quantum theory has revealed using the concept of complementarity. There is a contradiction in the idea that a quantum is both a wave and a particle at the same time. However, the concept that these two seemingly incompatible phenomena complement each other to form a single entity or world is called complementarity, or the principle of complementarity. Bohr is said to have liked using the taijitu, which symbolizes the ancient Chinese philosophy of yin and yang, as a symbol to represent complementarity. The concept is that yin and yang are one entity, and all natural phenomena are determined by their interaction. There is a concept called monism that serves as a pillar of Eastern philosophy. Generally, this is said to be a concept that opposes dualism, which is at the foundation of modern science. Dividing things into two categories, such as objects and mind, or nature and humans, is called dualism. In contrast, treating them as inseparable is called monism. Quantum theory presents a monistic view of nature, avoiding the dualism that separates nature and the observer. It considers nature, which is the object of observation, and us, the observers, as a single set. In my opinion, monism is not something that opposes dualism. Rather, I think monism is an approach that represents everything with a single value. It's similar to how a stronger light creates a darker shadow. In other words, even if you don't create a shadow, as long as you create a strong light, a strong shadow will naturally form. It's like the idea that once one thing is decided, everything else falls into place. Therefore, even if you see many results, in reality, there is always only one input. You start to see a worldview like that. Next is the thought experiment called Schrödinger's cat. The biggest conundrum in quantum theory is this thing called Schrödinger's cat. This Schrödinger's cat is one of the paradoxes in quantum theory. The purpose of this experiment is if the concepts of quantum theory are correct, right? Since there must be no contradiction between quantum theory, which is a theory of the micro world, and the previous physical theories, which are theories of the macro world, it becomes necessary to conduct experiments to verify this. The fact that the mathematical models and theorems we practically use between the micro and macro levels are incompatible is problematic when it comes to the pursuit of truth or the completeness of theories. It's troubling that there is a difference between classical physics and quantum theory, which are part of the same world, even if it's just a matter of scale. This Schrödinger's cat is a box containing radioactive material, a radiation detection device, and a poison gas generation device linked to the detection device. When radioactive substances undergo atomic decay, they emit radiation. The mechanism is such that if radiation is detected, the poison gas generator releases poison. And then, we put a live cat inside the box, which is a bit cruel. If the radioactive material decays at a certain point and releases poison gas, the cat will naturally die. Conversely, if the radioactive material has not decayed at that point, no poisonous gas is released, so the cat is alive. The result is obvious. You'll know once you open the lid of the box. The issue is how to consider the state of the cat before opening the lid. Whether this radioactive substance undergoes atomic decay can be determined probabilistically through quantum theory. If we assume this, when the lid is closed, the radioactive material is in a state where, for example, there is a 50% chance that nuclear decay has occurred and a 50% chance that nuclear decay has not occurred. Of course, if you make an observation, you will instantly know whether it has collapsed or not. However, when the lid is closed, we think of it as being in a state where both possibilities are overlaid half and half. The cat itself is a macroscopic entity, so it is not the case that it is undecided one way or the other. However, in the case of this device, the trigger for the release of poison is the decay of an atomic nucleus, which is a microscopic phenomenon, so it is in a superposition state where it can be either. In this situation, if you think about it normally, the state of the radioactive material and the state of the cat should be linked, right? At the same time, it can be considered that the macroscopic entity, the cat, is also in a superposition, just like the microscopic atomic nucleus decay, which is a radioactive substance. This is interconnected. So in other words, the moment the lid is opened, the state of the radioactive substance, meaning whether or not nuclear decay has occurred, is determined, and at the same time, the cat's life or death is also decided. I will say it again. It doesn't mean that we can't estimate the cat's life or death, or that we simply don't know, or that we can't determine it because we can't observe it. If you believe in quantum theory, you have to accept the idea that both states of the cat, being alive and dead, exist. This paradox hasn't been resolved at all. However, if there is a solution, for now, there is only one. That is the many worlds interpretation. The quantum theory up until that point was able to describe how waves propagate, but regarding the wave collapse that is said to occur upon observation, it was proven by von Neumann to be fundamentally unrepresentable. If observed, it is certain that the wave can be determined and observed at a single point. That being said, no one really knows if it is actually shrinking. There. Neumann starts to say that wave function collapse occurs within human consciousness. This part is a bit out there, but it means that a change in interpretation of that magnitude was necessary. The idea of the many worlds interpretation is to consider that, rather than collapsing, the wave continues to spread out. It is referred to as the many worlds interpretation, but it's what you might call a parallel world. Strictly speaking, I think it's different, but it's something like that. The universe repeatedly branches out with each possibility, and among the countless ever-increasing universes, one of them is the current universe we are in. This is ultimately a matter of interpretation, so it can't be said to be either correct or incorrect. Moreover, even if asked to show that evidence, it is probably impossible. It's an action that is impossible to perform, just like how you can't touch your right hand with your right hand. Strictly speaking, while it cannot be proven to be correct, it also cannot be said to be incorrect. That being said, the many worlds interpretation is also the interpretation that can be explained most smoothly. That being said, doubts still remain about this many worlds interpretation. When considering the earlier double-slit experiment from the perspective of the many worlds interpretation, it actually becomes a bit strange. In the double-slit experiment, when a single electron is sent towards the screen, the many worlds interpretation suggests that the world splits into one where the electron passes through the right slit and another where it passes through the left slit, right? The world will be divided into two from there, right? Two possibilities will emerge. If the world was split into two, an electron should only pass through one of the slits. This is because the electron that passed through the other slit is in a different world. That means only one side should be able to pass through, right? In that case, there shouldn't be any interference fringes created by the waves colliding with each other, right? This is a bit strange, isn't it? From the result that interference fringes were formed, it can be seen that an electron, which once split into a different world, completely diverged from our world into a completely different world. In other words, we end up observing a single electron that has two different pasts. One past where it passed through the slit on the left, and another past where it passed through the slit on the right. In the many worlds interpretation, the reason this happens is explained by stating that only when the two worlds result in exactly the same state, the matter that once split into these two worlds can overlap again, causing different pasts to create an interference state. Therefore, as in the experiment explained earlier, if an observation is made at one of the slits on the way to the screen, one of the electrons is affected by the photon, so the results of the split electrons will not be the same. In this case, the world that has split into two will not become one again, and it ends up being divided into two separate worlds, since only one result will appear. In this case, it means that interference fringes will not appear on the screen. That being said, it's fundamentally impossible for the phenomena we observe in our daily lives to result in exactly the same outcome without affecting anything around them along the way. Therefore, in the many worlds interpretation, the two branched states or worlds almost never overlap again in most cases. They proceed independently of each other, if this is indeed true, right? This is ultimately a matter of interpretation. Since it cannot be verified through experiments, the many worlds interpretation is. It can be said that there is no correct answer to interpretation problems, as it falls within the scope of whether the interpretation is convincing or not. Simply put, it's a trivial matter. In short, it's a matter of whether you accept it or not. It's the same in current physics. I would like you to understand that a little. Here's a bit of practical discussion. Once quantum mechanics began to reveal the correct structure of atoms, we were able to make sense of the periodic table of elements. The reason why elements with similar scientific properties exist at regular intervals, as well as how atoms bond to form molecules, and how molecules bond with each other, can be explained using quantum theory. In other words, quantum theory can be said to have incorporated science into physics, or alternatively, to have unified science and physics. There is also a phenomenon called superfluidity of liquid helium. This is a phenomenon where quantum phenomena appear in the visible macro world. When you cool down a gas called helium significantly, it becomes liquid. However, the properties of helium atoms change, and sometimes its viscosity, or thickness, becomes zero. A liquid with zero viscosity, when you pour it into a cup, will flow out due to its momentum. It can even crawl out, because it has zero viscosity. This is called a Bose particle, and such Bose particles exhibit a phenomenon that occurs when the waves of multiple atoms overlap at extremely low temperatures, causing them to behave like a single superatom. The phenomenon of superconductivity also falls into the same category of phenomena. I think it's fair to say that this phenomenon is like something from the quantum world becoming visible to our eyes. This is the phenomenon where the electrical resistance of a metal becomes zero, and the current that flows once is not converted into heat, allowing the current to continue flowing indefinitely. Next, semiconductors and the tunneling effect. In the microscopic world, the wave properties of electrons become strongly apparent. When an electron is viewed as a particle, it naturally cannot overcome or pass through a potential barrier, like a wall, that is higher than the energy the electron possesses. In the microscopic world, if the width of the barrier is narrow, electrons, which are not points but waves, can pass through the barrier with a certain probability, because they are waves. The probabilistic position of this electron allows it to do that. Therefore, since the electron is not determined, it can probabilistically reach that area, whether or not there is a wall around here, as long as it's thin. In theory, and according to calculations, that's how it should be, and that's how it actually turns out. That's how computers work. It's the image of the probabilistic position of electrons seeping out. This is causing us to reach the limits of integration for computer processors. If you make it too detailed, it ends up leaking. It affects the outside. When you see this, you can't help but believe that it is a fact that electrons spread out as waves, and their positions are determined regardless of barriers based on probability. About quantum computers. A quantum computer is a system that, unlike traditional computers which process information using only two states, 0 or 1, utilizes a superposition of 0 and 1, creating a state where it is uncertain which it is. By preparing countless such states, each holding information, it aims to perform massive information processing simultaneously. The concept of the quantum computer was thought up by a physicist named Deutsch. He says that the reason quantum computers can perform parallel processing is that calculations are carried out in multiple worlds that exist simultaneously. In other words, if quantum computers are actually completed, it is being said that this would serve as evidence for the correctness of the many worlds interpretation. I don't think this would actually happen, but that's what he claims. That being said, it's true that quantum computers still have many challenges to overcome, so it will likely be a little while before they can be used practically. This time, we provided an explanation of quantum theory. Much of what was mentioned pertains to the behavior of quantum entities, mostly. Quantum theory predicts the behavior of quanta and provides us with the most benefits in practical applications. As expected, it's difficult to feel like I truly understand quantum theory from the core of my being. Bohr said, "Anyone who is not shocked by quantum theory has not understood it. There are many people who can use quantum mechanics, but probably not a single person who truly understands it." In short, it is said that if someone hears about quantum theory and isn't shocked by it, they don't understand quantum theory. Until now, humanity has a history of making the impossible possible. Quantum theory is no exception, and new observation methods, mathematical models, and interpretations will continue to emerge. It is possible that this could usher in an era where the doors to parallel worlds are opened,